Number 4 is another trig substitution problem. This one, if you look at the top, you have the square root of x squared minus 3, and on the bottom you have x. And then this problem's a little different because we have some numbers there. So this is what's called a definite integral. We're going to have a kind of an answer associated with this, a number answer, if you will. So if you look at your notes paper, you'll see that in the chart that this is a secant problem. So it matches up number 3 on your chart for this one. So this one, let's write down some of the information so we can get started here. So this one, u squared is equal to x squared. So u is equal to x. So x equals a secant theta. So a is root 3 and then secant theta. So then we have to take the derivative because we need dx. So the derivative of x is dx. And then we have the derivative of root 3 secant theta is root 3 secant theta tan theta. So now we're ready to sub the stuff in. We're going to ignore the numbers. So we have integral, and then we have big square root, and then we have x squared. So that's going to be root 3 secant squared. So that's going to be 3 secant squared theta minus 3. And then we have a dx next, so that'll stay on top. So quantity root 3 secant theta tan theta, end your parenthesis, and we actually need a d theta there. So in the dx, we actually need a d theta, and then in our problem, we also need a d theta there. And then on the bottom, we have an x, so that's going to be root 3 secant theta. So now you can see the root 3 secant theta is going to cancel on the top and the bottom. So that's one thing we're going to simplify. And then the other thing is underneath the square root, we have the square root of 3 secant squared theta minus 3. So we're going to pull out a 3, but that's actually a root 3. So we can't actually do anything. So we'll just write integral root 3 and then another root on top. And then we'll write secant squared theta minus 1. And then we have a tangent left, tangent theta, d theta. And then on the bottom, we actually have nothing because the root 3 secant theta canceled each other out. So now we can simplify a little bit more. So now we have the square root of secant squared theta minus 1. So that's tangent squared, so it's the square root of tangent squared, which is tangent, and then we also have another tangent in the problem. So in this case, we have integral root 3 tangent squared theta d theta. So now we're integrating tangent squared. So the root 3 is just going to come along. Something in because we can't integrate parentheses, secant squared theta minus 1, and your parentheses, and then a d theta. All right, and now we're ready to integrate. So when you integrate secant squared, you get tangent, and when you integrate 1, you get theta. So our integral, when we're all done, is root 3 parentheses, integral of secant squared is tangent theta, integral of 1 is parentheses, put a bar there. So now what we have to do is we have to change those numbers around. You don't want to put root 3 to 2 because those were x values. So now you can see our values are theta. So what you have to do is you have to go back and figure out what theta is. So if you remember, we had an original equation. We had x equals root 3 secant theta. All right. So now our first x value is 2. So we're going to put a 2 in. 2 equals root 3 secant theta. Divide by root 3. So we have 2 over root 3 equals secant theta. So in this case, secant, where it's 2 over root 3 is pi over 6. Right? So the next one we had a root 3 at the bottom of the integral. So we have root 3 equals root 3 secant of theta. So the next one we just filled in root 3 for x. So you divide by root 3 and you can see you get 1. So 1 equals secant of theta. So where secant is 1 is at 0. So our other bound is 0. So now we go back to our bar, we have to plug in from 0 to pi over 6. So here we go. Root 3 parentheses pi over 6 minus pi over 6 and your parenthesis. Now technically you have to plug in 0, but when you do, you get 0. Tangent is 0, 0, and then you plug in 0 for theta, so you get 0. So you don't really have to plug that in. So the last thing you have to do in this problem is solve for tangent of pi over 6. So you have root 3, and then parentheses, the tan of 30 degrees is 1 over root 3 minus pi over 6 and your parenthesis. And that's pretty much all you can do. I mean, you could multiply the root 3 through and get a different answer, but for the most part, that's pretty good. Okay? So that's how you do that problem, which is a definite integral. So the next set of problems, they are called partial fraction problems. So these problems are a little bit different. There's no trig substitutions in these. These are just different ways of doing this kind of problem. So in this case, the integral of 5x minus 3 over x squared minus 2x minus 3, you can't do anything with it, okay? So what we're going to do is we're going to factor the x squared minus 2x minus 3. We're going to factor that. So we're going to factor the bottom, x minus 3, x plus 1. All right? So now what we're going to do is we're going to figure out numbers, A and B we're going to call them, that actually give us this same rational expression there. So the way we're going to write that is we're going to write integral A over x minus 3 plus b over x plus 1. And technically all of that has to be in a parenthesis because we need a dx on the end. Okay? So now there exists numbers A and B, which we're going to find that when you add those two things together, you actually get the original rational expression that we had. This is called a distinct linear because when you factored the bottom, x minus 3 and x plus 1, they are actually linear. So you have to look at them individually and decide what they are. So individually they're linear, and distinct means they're different. X minus 3 is different than x plus 1. So this is the first type of partial fraction. It's called distinct linear. All right. So now we need to set up an equation to find A and B, and then we're going to integrate it, which is actually the easy part. All right. So let's set up an equation. So we have 5x minus 3 over x minus 3 x plus 1 equals, and then A over x minus 3 plus b over x plus 1. Right? So now the way you solve this is you're going to get rid of the denominator. So you're going to multiply the whole thing by the common denominator, which is x minus 3 times x plus 1. Okay? So now when you do that, when you take 5x minus 3 over x minus 3 times x plus 1, and you multiply it by x minus 3 x plus 1, all the denominators cancel out with that numerator, so you're just left with 5x minus 3 equals, and when you take a over x minus 3 times x minus 3 x plus 1, you get a times x plus 1 plus, and then you take b over x plus 1 times x minus 3 x plus 1. The x plus 1's cancel, and you're left with b times x minus 3. All right, so now in order to solve this, it's actually pretty easy. What you're going to do is you're going to select numbers for x that make your life simple. So one of the numbers that you're going to select for x is -1, because when you plug that in for where the a is into a times x plus 1, when you sub in -1 for x, it's going to cancel the a out, and then we can solve for b. So you plug in -1 over here, so 5 times -1 is -5 minus 3 is -8 equals, you plug in -1 with the a, associated with the a, and that cancels out. So now you have to plug in the -1 down here with the b. So -1 minus 3 is -4 times b, which is -4b. And then divide by -4, so you get b is 2. All right? So now once we know b is -2, we choose another x value that's going to cancel out, in this case, the b's, which is 3. So choose x equals 3. So then you do 5 times 3, which is 15, minus 3, which is 12, equals, and then when you plug in 3, you get 3 plus 1, which is 4. 4 times a, which is 4a. The b cancels out, so then you have 12 equals 4a, so a is 3. So now you're ready to do your integral. All right, so now we have a and b, and we're ready to do our integral. All right, so your integral, parenthesis, you have 3 over x minus 3 plus 2 over x minus 1, end your parenthesis, and then a dx. So now you're in business. You can integrate that. Both of these are natural log integrals. So the integral of 3 over x minus 3 is 3 ln absolute value x minus 3, end your absolute value, plus 2 ln absolute value x minus 1, end absolute value, plus c. And you have your answer then. So we turned it into something you can integrate. So the other one that we're going to do is it's also a linear, but this one is repeated because you can see in number 6 that x plus 2 is linear, but it's repeated because you have 2 of them. So you have to do this problem a little differently when you set up your integral. Okay, so let's do that one. So let me erase room here. All right, so the way you do a repeated linear is similar. All right, so let's set up our integral. Integral, parenthesis, a over x plus 2 plus b over x plus 2, the quantity squared, end your parenthesis, and then a dx. So since it's repeated, since it's squared, you do x plus 1, or excuse me, x plus 2 to the first power, and then you do x plus 2 to the second power over a and b respectively. If it was x plus 2 to the third power, then you'd add a third one. You'd add c over x plus 2, the quantity cubed. So now you set up your equation the same way. So you would do 6x plus 7 over the quantity x plus 2 squared equals a over x plus 2 plus b over x plus 2, the quantity squared. So now this one you're going to multiply to get rid of the denominators in all of them. You're going to multiply by x plus 2, the quantity squared. All right? So when you do that, you take 6x plus 7 over x plus 2 squared times x plus 2 squareds. They cancel, and you're just left with 6x plus 7 equals, and then a over x plus 2 times x plus 2 squared is a times x plus 2. You have 1x plus 2 left. And then plus, and then b over x plus 2 squared times x plus 2 squared. The x plus 2 squared cancel, and you just have a b. All right, so now this one you solve similarly in that you choose x's that make your life simple. So for instance, let's choose x equals -2. So when you choose -2, 6 times -2 is -12, plus 7 is -5. When you plug in -2, you get -2 plus 2, and that's going to give your a as 0. So you don't have to worry about the a. And then the only thing you have left is a b. So b is -5. So last but not least is you're going to choose an x value then, that anything you want to solve for a. So it doesn't really matter. So I usually choose x equals 0. That's a good number to pick. So 6 times 0 is 0, plus 7 is 7. And then you plug in 0. 0 plus 2 is 2. 2 times a is 2a. So you have 7 equals 2a. And then plus b. So we know b is -5. So now we can say 7 equals 2a minus 5. So then you can add 5, and then you divide by 2. So a is 6. All right? So now we have our a and b, so now we can do our integral. All right, so we have integral, parenthesis, 6 over x plus, what is it, x plus 2, right? Yep, 6 over x plus 2, plus negative 5 over quantity x plus 2, the quantity squared, end your parenthesis, and then a dx. So now when you go to integrate this, the integral of 6 over x plus 2 is a natural log. So you get 6 ln absolute value x plus 2, end your absolute value. And then when you integrate negative 5 over x plus 2, the quantity squared, that's going to be a power raising problem. So x plus 2 is to the negative 2. So when you add a power over that power, you get negative 1. So that's going to turn that negative 5 to a positive 5. So the rest of your integral is plus 5 quantity x plus 2, end your quantity to the negative 1 plus c. So your answer is 6 ln absolute value x plus 2, end your absolute value, plus 5 times x plus 2 to the negative 1 plus c. So that's what's called a repeated linear quadratic or partial fraction problem. So the next one we're going to do, number 7, I'll stop the video. This is distinct linear, and this also has a quadratic in it, which makes it a little more complicated.